So the rate of a chemical reaction, it measures how fast the reaction is producing the product or how fast the reactants are getting used up. It's the same thing, you're just looking at one end or the other. How fast are the reactants disappearing or how fast are the products appearing? So if we have a reaction with a fast rate, here we've got the blue thing plus the red thing is making the green thing. And here, let's say this is time 0, maybe this is 15 seconds, 30 seconds, 45 seconds. We see that within 45 seconds, all of the reactant has reacted and is all turned into product. This reaction has a slow rate, same time span. We get to 45 seconds. Now there's product here, those little peach-colored things, but there's still a lot of reactant left as well, because that reaction is proceeding more slowly. Does that make sense? There's a lot of stuff here where I got some good head nods there. If it doesn't make sense, I want to know, because if something doesn't make sense now, in 3 slides, it's going to be much worse, right? So we want to understand as we go along, and then it's actually kind of beautiful. If you get lost, it's just painful. So defining rate. Well, we're familiar with rate in terms of like a rate of speed, a travel. How fast did you go on the freeway? I was going 70 miles per hour, right? So speed is a rate. It's distance traveled in a given period of time. So 70 miles per hour means that in 1 hour, I would travel 70 miles. I can go that fast without actually going 70 miles because maybe I only drove for 10 minutes. I'm not going to go 70 miles, but if I had driven an hour, I would have gone 70 miles. So we can define speed as a mathematical equation, the change in distance divided by the change in time, or delta x over delta t. Delta means the same thing it did in Chem 1A. It's the change in, almost always the final thing minus the initial thing. So we can look at the rate of a chemical reaction as the change in the amounts of reactants or products divided by the change in time. So, oops. Oh, that's right, okay. I gotta do this. You know how long it's been since I lectured to people? Almost 2 years. It's crazy. So change in concentration divided by change in time. Does that make sense? So it's the per unit time, just like how fast your car's going. But instead of looking at a position along the road, we're looking at the concentration. It could be, we can look at the reactants, because they're going down, or we can look at the products as their concentrations increase. So let's look at this reaction. It's in the gas phase. So we have 1 molecule of hydrogen reacts with 1 molecule of iodine to form 2 molecules of hydrogen iodide. If we look at the concentration of hydrogen as the reaction proceeds, the concentration is going to go down, right? So that means that the concentration of hydrogen, the final one, is smaller than the concentration of hydrogen initially. So we take a small number and we subtract a big number and we get a negative number. It's going away. So change in concentration of reactants is negative because the concentration is going down. Going down, change is negative. But when we talk about a rate by convention is always expressed as a positive number. Now, you could say, if you're going north on the freeway, that's positive. I'm going positive 70 miles an hour. If I'm going south, I'm going negative 70 miles an hour. But we don't talk about it that way, right? Because we really don't care about the direction that much. How fast is it going? And so just like we always express speed as positive, we're going to express a reaction rate as a positive number. So if we look at the rate defined by the change in the hydrogen concentration over the change in time, we have to put a negative sign in front of it. Because delta, if you don't remember, these brackets here mean concentration. Usually molarity, but it's the concentration of hydrogen. We take the concentration at the final time 2, we subtract from time 1, and that is a negative number because the concentration is going down. The time is always going to be positive. And so in order for the rate to be a positive number, we take this value that we get, that total thing is going to be negative, and we multiply it by -1 to make it positive. Okay? We could also look at the rate in terms of the concentration of iodine. And again, it would be a -1 times the change in the iodine concentration, which is negative, divided by the change in time. Any questions? We can also define it with respect to the product. So the product is HI. Product concentrations increase. They go from smaller to larger, so the change is positive. And so if we express the rate as the change over time, change in time, we're going to get a positive number. So we don't need the negative sign. So the rate of reaction is related to the change in HI divided by the change in time. Now, why is there a 1/2 here? The rate of this reaction, there's only one rate. But we can end up with different changes of something per change in time, depending on whether we're looking at hydrogen or HI. Because for every hydrogen that reacts, we get 2 of these. So if we just looked at the change in HI over the change in time, this would be twice as big as the change in H2. Does that make sense? Because we're making twice as much product as we started with reactant because it's coming apart into more pieces. So we use this little coefficient in here, and that's related to the stoichiometry of the reaction. I'm making 2 of these, so this is 1/2. It's 1/2. So that this rate is the same whether I define it by the hydrogen concentration, the iodine concentration, or the hydrogen iodide concentration. Because the concentration of HI increases twice as fast as H2 and I2 decrease. We need a single rate, and so the definition of rate with respect to each reactant or product has to reflect the coefficients. Is that scary? Some of you are like, oh, cool, graphing. And others of you are like, what is that? It's okay. It's taking something that's very abstract and making it visual so we can see it. I'm a very visual person. I have what I call chemistry land in my head. And for these things that you can't see, because that's the frustrating thing about chemistry. If you're wanting to study a molecule, it's too small, you can't see the pieces. So what do? We use models, right? And then I have pictures of models in my head, and that can do way more cool stuff than just the simple model in my hands. So we like to make things visual so we can see trends and see how things are changing. So what this graph is we've got concentration in molarity on the y-axis as a function of time in seconds. And we're looking at two different things here. So this is the concentration of the product. It's starting with none, and it's going up as time goes on, right? Concentration is increasing. This is the concentration of one of the reactants, H2. It started at 1 molar, and it's going down because it's getting used up, okay? So we can see the progress of the reaction here. The rate of the reaction is the slope of the line. And you'll notice the slope of the line is changing as time goes on. And that's why we start out talking about reaction rate because that's easier to understand. But an actual reaction rate is not very meaningful because even in the same beaker, as soon as the reaction starts and you've got products being formed or reactants going away, the rate changes. So if we look at how fast H2 is going down, that's the slope of the line. So we could take this point and this point. And remember, slope is the rise divided by the run, or the change in y divided by the change in x. That's not an x. That's not an x either. There. So if we wanted to look at the change in concentration, we can find, I think I pointed to the wrong thing. They're using this point and this point. And so you can take 2 points on that line and calculate the difference on the y value and divide by the difference in the x value. And that gives you the rate of change at that point in the middle, but it's constantly changing. We can also do that for the product. The product is increasing with time. So here again, we can select this same bit of time here, or point in time, and choose a couple of points here and draw a line and calculate the change. I know what I forgot. I forgot my calculator. That's pretty bad. Let's just look at that real quick. So if we calculate the rate for this, the rate going on there, the change was 0.56 moles per liter in 40 seconds. Thankfully, I do have a phone that does this. So I get 0.014. And then what do we do with those units? They don't cancel. We just keep them. Molarity per second. It's okay. And if we look at this guy down here, he's changing negative 0.28 moles per liter, also in 40 seconds. And that gives me 0.00, well, negative 0.007 molarity per second. Why are they not the same? Because of that too. Yeah, the product, we're making 2 moles of product for every 1 mole of reactant. So we're making that twice as fast. So that's why the rate is going to equal 1/2 the change. Well, this is getting very messy. 1/2 0.014 molarity per second. which would be 0.007 molarity per second. Down here, this one's negative because it's decreasing, but we always express rates as a positive, just like we always express speed as a positive. So here, the rate, because this is a reactant, is negative times 0.07. And so that rate is also 0.007 molarity per second. Any questions? Yes?
So you can't leave it as a negative, it has to be a positive?
If you're looking at the rate of the reaction, it has to be positive. If you're talking about the rate of change of hydrogen, that can be negative because it's going down, right? But the rate of the reaction has to be positive. And it's defined so that whether we're looking at the reactants, any of the reactants, or any of the products, we can just look at one of them and calculate the rate because there's just only one rate. Any other questions? So the average rate is going to decrease as the reaction progresses. So here, time, 0, 10, etc. The concentration of H2 is going down. If we look at the change in the concentration, that's this one, 0.819 minus 1, 0.67 minus 0.819. We see that we're getting negative changes in concentration, but these are getting smaller as time goes on. The time interval here is the same, so when we calculate the rate, we see that the rate is decreasing. It started out at 0.018, and it got slower and slower. At the end, it was 0.003. And that's what we see when we look at this. When we look at this curve, right? The slope here is steep. So part B of this problem is determine the rate of change in the concentration of H plus during this time interval. Well, we kind of need that information from back here. If I remember correctly, let's see. Oh, come on. There it is. 4.40 times 10 to the minus third meters per second is the rate, right? The average rate. So here, we're wanting to find how H plus is changing. So we're looking for the change in hydrogen ion concentration over the change in time. What we know is that the rate equals 0.00440 molarity per second. How is rate defined in terms of that reactant hydrogen ion? The rate equals what? Do we need a negative for the reactant or for the product? Negative for the reactant because its change is going down, it's negative. So negative, and then what do we do with this 2? Yeah, so put it under 1, so the reciprocal, 1/2 delta H plus over delta T. So this is what we're trying to solve for. We can treat this thing as one variable, right? So multiply both sides by -2. And we'll get delta H plus, that's messy, over delta T is going to be negative 0.00880. So to get rid of the negative sign, multiply by negative 1, and then multiply by 2 on both sides, and I get this. That make sense? Some of the problems we end up doing in this class are very simple algebra, but the numbers are weird looking, like 0.0040 or 00440. They don't use that in algebra class. You know, they use like nice numbers, like 5. And then what we're solving for here is not just like x, right? It's this big messy looking thing. But that's the thing, that's the whole thing. And so solving this looks weird, but it's actually super simple. Good, got that one right. Predict the rate of change in concentration of H2O2 and I3 minus during this time interval. Well, there's 2 ways we could do it. We could do it from the rate. Or we could do it from the change in the hydrogen ion concentration. So I'll show you both of them. So we want to find the change in H2O2 over the change in time. And so we could do it the same way we did the last one, where we've got the rate, and the rate equals what in terms of H2O2? Yeah, negative, and if you want to be picky about it, negative 1 over 1, delta H2O2 over delta T. So then this is just negative 0.0044. Right? That makes sense? So with a lot of these problems, there's more than one way to solve them. And which way you think is the easy problem just depends on how your brain is wired. So I'm going to go with a different color here. So we know that the rate is equal to negative 1/2 delta H plus over delta T. And it's equal to negative delta H2O2 over delta T. Right? And then we could put in the I minus and the I3 minus and the H2O and list them all out, but we don't need the others. I have a number for this. So I can plug that number in, negative 1/2 times negative 0.00880 molarity per second equals negative delta H2O2 over delta T. That's what we're trying to find, right? So we can multiply both sides by negative 1. Now we've got that, and then just do that math there, and we end up with negative 0.00440 molarity per second. Any questions? Sometimes it's tempting. You recognize, oh, it's just real simple, and it's tempting to just do the whole thing in your head and write down an answer. But especially when you've got fractions like this, it's so easy to just make a silly mistake and end up multiplying by 2 instead of dividing by 2. And even if you don't need to show your work in order to come up with the right answer, being able to show your work clearly is an important skill. And so we're going to practice. Any questions about that one? So this one's a conceptual question, meaning we shouldn't have to really do much math. Here we have a reaction A plus 2B going to C. Under a given set of conditions, the initial rate is 0.1. What is the change in B over the change in T under the same conditions? So this is one where it's really tempting to just think about it and write down an answer. Especially when I'm lecturing and I do that, I get it wrong. So what we want to make sure is that we remember the rate here in terms of B is negative 1/2 the change in B over the change in T, right? So if the rate is 0.1, then what does this equal? It's negative 0.2. So let's just actually do it. And so we have to multiply by -2 on both sides. And that's the answer. You see how easy it is to just like, you see 1/2, and so you're like, oh, well, I'll divide this by 2, and there's my answer. But I did the opposite. So I always put a question like this where you have rates and changes of individual components in the reaction. And it's actually very straightforward, but a lot of people get it wrong. So how do we measure the reaction rate? We have to be able to measure the concentration of at least one component in the mixture. So we can find the concentration at the start and the concentration at some time, so we can calculate the change in concentration conversation. So there are two ways to approach. For a fast reaction, meaning something that's going to be finished in less than an hour, it's best to use continuous monitoring of the concentration. But if you have something that's going to take like several days to complete, then you want to do sampling at various times. So I'm not going to test you on these techniques, but I just want you to get an idea and appreciation for how kind of challenging it can be to measure the concentration of something in a mixture. So one way is to use polarimetry, and that measures the change in the degree of the rotation of plane polarized light. So if you have a chiral compound, it will bend the light. You can measure that. As that reacts and becomes non-chiral, then the shift changes. And so that's, in very special circumstances you can use that. The total pressure, so we learned in Chem 1A that the total pressure of a gas mixture is the sum of the partial pressures. And it's equal to the stoichiometry comes into play there. So here if I've got, it's hard to explain. But let's say this one is, as two of these react, I'm going to form three of those. And so the pressure is going to increase. And it's going to be a 2 to 3 ratio. You have to do some math and figure it out. Spectroscopy is another thing. Solutions absorb light. And we see this especially in colored solutions. Why is Mountain Dew yellow? Because they put yellow food coloring in it. Well, why is yellow food coloring yellow? Because it reflects yellow light and absorbs other wavelengths. And so you can use a spectroscope which measures wavelengths of light. You can measure how much light is coming through, and it's basically telling you how colored is the solution, how intensely colored. And that's related to the concentration. So it might get darker in color, it might get lighter in color, but that can be used to measure the concentration. It's not what I meant to do. So here's a schematic of a spectrometer. So you need a light source, and you don't want this whole big blast of light, so you run it through a slit so you get a more manageable section of light. You run it through a monochromator, which is basically a prism that separates the light by wavelength. And you can choose which one of these wavelengths you pass through the sample and measure in the detector how much of that light was absorbed. And so the more light absorbed, the more of that substance is in the solution. In this reaction that we were talking about, hydrogen gas and iodine gas, hydrogen gas is colorless and hydrogen iodide is colorless, but I2 is a really pretty violet color. So you can measure the absorbance of the gas mixture. I was going to say air, but it's not air, it's a gas mixture, and use that to determine the I2 concentration. One of the fascinating and challenging aspects of scientific research is, especially in things like chemistry, we are trying to study things that are too small to see, right? So we can't just go in and measure it directly. That'd be too easy anyway. We have to find another way. And so a lot of these techniques, analytical techniques, are finding a way around this thing being too small to measure. So here we're using the absorbance of light, because the more particles there, the more light it's going to absorb. And that correlates to concentration. What about periodic sampling? Well, you can take an aliquot from the mixture at certain times. What's an aliquot? Well, it's a sample that you take out of the reaction mixture. It's a fancy word. So you want to take just a very small part of the whole reaction, because if you took half of it, then you're messing it all up, right? So you're going to take a little sample away at a certain, you measure the time when you took it away. Now you can either analyze it immediately, or you can do something to stop the reaction there. But if you take that aliquot and don't do anything with it for a while, the reaction is going to keep going on in your aliquot, right? And so you're not going to be measuring what you thought at that time. But we can do quantitative analysis on the samples. Titration is one thing that could be done, or gravimetric analysis, which is typically converting something into a solid, precipitating it, and then measuring the mass of that, or gas chromatography. So I think there's a picture of gas chromatography. Yes? So gas chromatography is a way to separate the components of a mixture. So we have a carrier gas supply, and we have one of these instruments in the instrument room over there. So this carrier gas will often be something like helium or nitrogen, something inert. And so we have this gas going through a column, and this column is a long, really skinny tube. And the composition of the tube, depending on the composition, it might attract things that are polar, or it might attract things that are nonpolar, or it might play on some other difference in those compounds. But the different components of the mixture will have a different affinity for this column. Do you remember the paper chromatography lab? So we had a marker on a little piece of paper, and you stick it in a solution, and the liquid rises up, and it separates into different colors, right? Well, that's paper chromatography. This is the same concept, but instead of paper, you have this tube. And the gas is like the liquid, which is carrying your sample, and some of the sample is going to really like the column. And so it's going to go through here really slowly. And that's going to be like this peak that's at the end. And some of it's going to like the gas better than the tube. And so that'll come out sooner. And so you can get them to separate so that when they hit the detector, you're only looking at one component instead of all of them mixed together. And so there's a whole branch of science around chromatography.